I think I'm hearing. Yeah, there we go.
Oh, that's good. I thought I was going deaf.
Okay. Yeah, so basically, I mean, the idea is that a lot of my research, at least early on, like when I did my PhD, we had a rover, like a planetary rover, so for space, that could move in different ways, and I was interested in the idea of like that there's no one strategy that works all the time, and you have to have multiple options, but you have to know when to use your various options. And so develop something during my PhD where it's like you decide in advance what you think is going to be the right strategy, and you monitor as you do it to see whether how well it works, and decide, okay, you know, it's time to change your strategy. Then up to that, the navigation aspect is like, what do you need? What representation of the world do you need? What strategy of moving around you need? And essentially, I sort of adapted those ideas to perception when I came in. It was like, oh, CFR, we have all those cool sensors. So it's one of the places where you could have a bunch of sensors you wanted. So you had, like on this guy, that's probably one of the biggest set of sensors that the vehicle had out there at the time. They got multiple sea gliders. We had a great radar from Graham. We got an infrared camera, visual camera, all this stuff put together, and they all obviously have, you know, good things and bad things. And so how do you adapt, how you combine this information between all the sensors to make the best of all the words, if you like. That was kind of like, and yeah, I was saying this is one of my favorite, all-time favorite research pictures that I can't help to show every time. This is just blowing some dust with a compressor, put some dust in there, and that's a lot of fun, and trying to see whether we could navigate around this. A little bit more recently, when in QUT, so we looked at this problem again, but this time I guess we didn't have a good radar, like we didn't have ground with us, we didn't have perfect radar this time, and those radars are still pretty expensive. They do a good job, but sometimes you only have your 3D lidars. One of the differences that came up is that 3D lidars that have native echo and a better reflectivity as well, from like the sea laser we had before that was kind of zero everything, maybe sometime a value in between that and nothing. So we couldn't do much with that. Those sensors got better and get us a bit more stuff, and then there was deep learning, of course, started to do well with point clouds. So we started to be able to basically recognize when you have particles in the air, like you heat particles in the air, and that's what you see in your scan, as opposed to all the rest. And so we were able to have that detection. So you see that detection there in white as a voxel form or in a point form, depending on how much computation you can afford to put on the problem, and how much resolution you need necessary to do this. And this is good as long as usual. It's like the idea is in our case, it's often these are the type of thing that the platform can take as an obstacle. It's not an obstacle. You don't want to be stopping or moving around just because you have this in front of you. So if you can clear that and say that's particles in the air, as long as you see well what's happening behind it, obviously, hence the multi-echo, which is interesting. If you can't see anything through, you don't want to drive blind either. But that's something that works reasonably well. Pure lidar, we did that with so the student Leo studied that with stereo as well, and if you combine the two, it's even better. Well, obviously it's not always obvious. I shouldn't say that, but in the good cases, if you combine the two, that's even better, and you can do some some reasonable estimation of the certainty out of this, but too much into that. One of the things I did back in ACFR that I've started to do back in France, so it's been a long time going, and it's terrain traversability estimation. So for those who may not know what that is, It's basically you get your robot or rover or whatever mobile vehicle. You're looking at terrain in front of you, and you're trying to figure out how difficult it's going to drive over this. So from the geometry perspective, we do that pretty well these days. What you need to do so often is filling a few gaps like this, because like there's tends to be some gaps in your presentation. The second challenge that comes in is the fact that the terrain is usually assumed to be rigid, and sometimes it's not, especially in soft soil, like in those applications like rovers. So what we did back then is try to predict the deformation of the terrain as you go over it. Now that works reasonably well for things that where the correlation essentially between the deformation and the geometry is there, which means that things like, and potentially some of the semantics. So for example, if you have a pile of rock and you understand how those rocks are put together, you may be able to know that when you're gonna go over it, that pile of rock might collapse, or that piece is gonna change form. So, however, if you look at a sand dune and you don't know how soft or what's supporting under it, etc., then that geometry is not telling you that much. It's telling you, okay, that sand dune is making it more difficult, but because of the geometry purely, how much deformation you might have is extremely difficult to. So it's one of those things where we thought when we did that we could predict with soft soil and rocky terrain, etc., and we had to toward the end restrict to basically say that works for rocky terrain, but we can't still do really much about the soft soil, because that looks too much the same when you look at it visually. That's just like couldn't tell. And then back then again, that's showing that because we did some more work on this. Like I was driving through vegetation. That's always one of those things. And again, should I put out the whole video that was so landmark of the time where you had that big, the big Argo robot. For those who may have seen it back then. You don't have any of those stuff.
Argo's a lot of fun.
It should be in the museum again.
Yeah.
The museum of platforms. So we need. And he was driving in Maryland, and then you had those grass tufts like this on the ground, and you would just swipe around like this. He was scared of it. It's quite pathetic. Massive vehicles like grass. So we said we had to do something about it. And then of course when we did something like this, now it's getting really challenging, because okay, that's actually scary because you know what's in there. So semantics, of course, is very good at saying this is vegetation, this is a pile of brick, etc. But then when you have something like this behind vegetation, that's something you don't see, and semantics is not going to help you there. So we did some work back there with a UWB radar that could penetrate through the vegetation to clear out some of those obstacles, but you have to be really sure that you want to clear the obstacle. Some people say this is not an obstacle, you can go ahead. Now, unfortunately, those radars they don't make them anymore, and it's really hard to find those type of radars that can do those type of application these days, which is a bit disappointing, because we're totally capable of doing some better ones. But that's where the reality sometimes hits you, like you really want to push that research, but you need the sensors to be able to do it, and if no one produces the sensors, then try to do them yourself, but you're going to spend years to develop them. Some of our colleagues tried that, that's here. So we still developed some new work on terrain traversability estimation. So just for context, this one I can't say it had a lot of groundbreaking research as such, but worked with Rheinmetall to develop autonomous navigation for transport vehicles, and being able to exploit the fact that semantics is getting really good, semantic segmentation, so you can train a vehicle to recognize some of this terrain like mud and grass, vegetation, etc. Setting up some classes as usual fairly arbitrarily, but you exploit the pre-trained models and you just refine them, you can get something. So not to get too much, nothing fantastic there. There was combining this with then the traditional metrics such as the geometry characteristics, slope and recursiveness and things like this, and you can get a pretty decent system there. one of the interesting aspects of our research beyond what you build up doing in real time and all this is what is difficult for a vehicle is a very I'm not going to say subjective metric or subjective measure, but it's something that really depends on the context. So in this context, I was defense application. If you are like transporting your stuff in friendly territory and have time, etc., you can basically think everything is scary. You need to avoid those puddles. You need to avoid things because you never know, you could get bogged down, right? But if you're under enemy fire, then that's a whole different story, right? It's like, what's actually dangerous is all relative. So you reconsider out of the context what you consider actually risky. Some of the recent work we did is, again, so looking back at driving through vegetation, dense vegetation, which is still a open problem. But this time not having radars penetrating, etc., but having better capability or better lidars for a start. And again, exploiting the fact to have multi-echo, which is not a solution to anything as such, but that adds an extra piece of information. Having a system that is, so this vehicle here is, this work is collaboration with CSIRO. This work we use in there one of the CAT pack, which is basically that pack that's rotating, well, has its own rotation, a normal one, and an extra rotation the other way, an angle, and building accurate map environments. Very good LiDAR SLAM, I think if I can confirm that. Almost as good as the one you did, what was that, 10 years ago? Something.
I was doing SLAM at QCAT as well.
Yeah. So that's a really good system for, well, you probably know that the team at SIRO was at the DARPA Safety Challenge, finished second, and had the most accurate map by quite margin. So that just says something. That's really top stuff. So when you have access to something like this, you can really rely on super accurate 3D representation of your environment, and you can worry about all the things, even though it's not perfect, but and especially in an environment like this is that those slight imperfections are costing you, but it's a good base to work on. So we can build some nice representation, voxelize or not, and then exploit some of the also improvement of the sensors I mentioned before, where the reflectivity is much more calibrated, better calibrated, and more meaningful. You have the multi-echo. You can do some ray tracing over a GPU, which costs you, not much compared to what we used to cost you. So that's also nice. And so how when we're looking at this, it's basically, so can you drive through vegetation? It's a question, or can you essentially push through some of that vegetation as you go, rather than being blocked by it? So initially, the system was actually going to have force sensors on front or bumpers and basically evaluate how much resistance they had to put, and we're trying to associate that with what we see. In the end, didn't quite get to that. As often, you don't do as much as you expect it to do. That happens. It's okay, because it tends to be harder than you think. So we didn't have that, but we're still learning basically labeling the asset based on what the vehicle experiences. So when we stuck with something, then it's the front of the vehicle is not traversable, and when we can traverse through that, it is traversable. Really straightforward in that sense, although we'll see that there are some challenges with that. One of the interesting things in our work is actually labeling. So for anyone who does some machine learning related stuff, you know that getting good ground truth is accurate ground truth is essential. And in many applications, we can't quite get that. And so you have to consider how uncertain your ground truth is, or you have to, or try to make it as good as you can, really understand the limitation of it. So when we get, the easiest way to label something like this is to give the point cloud representation and colorize it and give it to someone and say, okay, now you label this and you declare things are traversable now. Humans are fairly good at doing this, but we're not that good. That's the problem. So we make lots of errors. So it turns out compared to having the vehicle actually testing it, it's not quite as good. And so you get plenty of data labeled by someone, which is not great, or much less data labeled by a robot, which is much better. And then you look at, okay, what do we do with that? So some of what we do there is trying to look at, depending on, we do one or the other, or we do some proportion of one or the other. When does it start to hurt the system to have too many label data, or not enough of the robot level data? That's always an interesting conundrum with that. Actually, let me just go straight to that and talk a bit more the labeling before I go into the rest. So one of the things we're doing is we were kind of naively initially drive around, and then basically when we have something that's not traversable in front of the robot, we declare the voxels that are right in front of the vehicle as untraversable, because you kind of don't know, well, unless you really look at having, let's say, the force sensor at the front that has enough ability to know where the resistance is. You don't know exactly what has actually stopped your robot. But if you do this, you tend to label a lot of points that are not traversable, some of which are actually traversable. I don't have that many levels there, so you don't want to make that mistake. When obviously all the points that are under the footprint of the robot are considered traversable, because if you're there, that means you were able to get through, right? So what we had to do is, in the end, instead of having a collision map like this, we had a probabilistic one where we put a filter on, we basically do Bayesian filter on it, so that when we revisit places, we can reconsider essentially and refine the label that we put on there, whether it's traversable or not. And because with the traditional approach, once you declare traversable, pretty much you're stuck with that and make a lot of things. So, it's all the things. It's meant to be ground truth, but that ground truth comes out of a probabilistic map, right? So is that the ground truth still? Could argue, maybe not, but we find first, from our point of view, this is the outcome that is better than the one that is deterministic, supposedly, but it's actually incorrect. So how good it is, that's always a great question, and depending on the discretization of that thing or more other things, and we haven't quantified that as well as we sometimes could. The data set is published, by the way, if you're interested. Okay. So when the first version we did that was with features. Since the version, we don't actually use features, and that satisfied the learning people better. Not sure that satisfied me better, but anyway, so I like to talk about the feature one. So for those who may have done some of the things, some of the simpler one is occupancy. So occupancy map, occupancy grid, or occupancy voxels. How to do this probabilistically reasonably well based on the principle in there. This one is an interesting one which takes into account things like permeability. So that row here is a permeability, which is so some of the other ones, so properties of the intensity that you find on the points that fall into that voxel, and again some of the properties of distribution of those points in there. The permeability is really interesting because that's the type of thing that starts to tell you something about the vegetation. So again, the ray tracing thing. When you hit something, so first you may hit it with the first return or second return, but that tells you where you hit something, but that tells you also all the voxels you went through as you did this. And then you can record that information and saying, okay, I've been through that voxel this time, right? And then sometime later I hit something in that voxel. It's like, okay, now it's a voxel where sometime it gets through, sometime I actually hit something. So that tells me something interesting about type of vegetation and stuff like that can happen in there. This tells us something about the shape of what we have in that voxel, and the hope is that we can capture things like branches versus leaves and stuff like that. Then we have the multi-return, which can, I guess it tends to tell you something about you were able to have. It's not your last return, it's the first one, so it's probably something I can penetrate through with some of my light beam. So that means it tends to be things that are less rigid, except for the edges of things that are rigid, of course, but you hope that they are captured at enough resolution. The coloring is one that helps for the semantic aspects. I'll come back to that property of the coloring. And the agency is just some properties around the voxels joining, because the shape that we're talking about, like branch or leaf, sometimes you need the information on the neighborhood voxel to actually understand that shape. It's not enough to decide this. Yeah, so in Queensland, we have lots of rainforest things, so we can easily take the assets that are very challenging, like this. You see that at the back of QCAT, on the sides. Let's have some dense forest in there, are relatively, it's not a jungle, but it's quite complex. And then the idea is that you classify traversability on there. So it's actually still a relatively simple binary classification, traversable, non-traversable, with some uncertainty that you can put on that. The probability of being traversable is what's on there. Let's see if that's gonna play. If I can find my cursor. Wait, my drum, and that's playing. No. This one. That's not showing the last screen, of course. So so in that first version, it's post-processed after collecting nice scans of the environment, and we have a nice view. In the newer version, we're actually doing that pretty much all the
Power
time.
supply. Your battery is about to go flat.
Oh, thank you. Laptop's getting a bit old. Yeah, we are now doing that that same system kind of real time. So we just do the traversability as the information comes, and actually we found that we are able to do that almost as well, even though we don't have a full sort of picture. As soon as you have just enough data to process that, it's kind of like those branch type trunks and things, that's fairly easy. All the bushes and stuff, that's where it gets a little bit harder. And some of what tends to be hard still with this one, but I can complement with traditional approaches, things like logs on the ground and things like this, like what's happening on the ground. But that we don't actually use the traditional like ground terrain traversability estimation that I showed before. So we complement that with the system to do that. This is more meant to be evaluating the vegetation above the ground to see whether you can actually get through that or not. And that does a pretty good job in that sense. I have to go like this. Okay, that's a beautiful looking table with results. Who knows about the MCC score? Nobody knows about the MCC score? Who knows about the F1 score? Oh, everyone. Okay, can someone tell me what the F1 score is? Not you.
I don't know what it is.
You don't use it ever? No, you don't.
It's a combination of precision and
Yeah. You know the formula. Something like that. Yeah. Does anyone know what's the biggest flaw of F1 score? Why? So F1 score is like, if you do a binary classification problem, someone was going to want the F1 score, right? And the F1 score, back in the day, people would put a true negative, true positive something, and essentially, we'd sort of favor the precision of the recall, and I was always debate like, yeah, you need both good or what's like, depending on the application. The F1 score was meant to sort of put that together. Basically, if it's high, then both your precision and recall are high, and I mean, it's your performance is good, yeah. But it has one flaw that I think most people tend to, and I didn't realize until recently, right? So it's not your fault. Most people use it and all good, etc. But in an application like this, it's super critical actually, and that's why we're using the MCC score. And we we're taking some risk there because that number is lower than the F1 score. So it's like, oh my God, what are we doing here? We're shooting ourselves in the foot, right? We may have actually according to the reviews, but it's one of those times where I was like, we think we're doing the right thing here. So number one, the F1 score has one major flaw.
False negatives. That doesn't take into account one of those, right?
Exactly right. Yes. So the choice when you do your classification, you intend to choose a positive class and a negative class. Yeah, that choice is absolutely critical to the F1 score. So that one favors the true positives basically. And if you have very little, so if you have plenty of positive classes and not a lot of negative classes, you can easily get a very high F1 score. But you could do an absolutely terrible job on the other class, and that wouldn't show. And that's the critical one. So in traversability estimation, you tend to do like positive is traversable, negative is non-traversable, so that you don't have a lot of samples not traversable. So that goes in your favor, and you sort of like do that, then you get a high score, right? So that's the type of thing that's been criticized more recently, and some people have argued you should use an MCC score, which is the matches correlation coefficient. One of the things that doesn't help, it's a correlation coefficient, so it's between -1 and 1. It's not between 0 and 1. 0 is chance, and basically you're trying to have high score or backward score. And so, yeah, so when you do that, you get much lower values because it's actually much harder to get a high MCC score than a high score for particular that. And that score is completely balanced on the two classes. So like, which one you choose, and positive or negative, doesn't matter. It works out nicely. So look it up. I recommend it if you're doing binary classification. You may have to argue to others why you're doing this, and unfortunately, as a result, we still have to put F1 score because they want mistakes. And if you only put MCC, they're going to tell you, why do you put MCC? That because your F1 score is low. No. So it's, some of those things you have to consider for experimental validation. Anyhow, closing that parenthesis, the main point is, I guess, so that system, you get different version of that with different type of ablation analysis, where you include some of the features and a lot of them, see the performance in different cases, etc. I'll let you do that. And I'm realizing that I didn't include the latest result in here. Yeah, that's the older version. So what I was meant to add there is that we're also doing, so now we're doing a version where we don't explicit the features, we're using sparse correlation neural networks to basically track the information, not having to explicit the features that we had there before, doing that kind of on real time. And so the pure LiDAR-based method is getting good enough that adding the color doesn't always help. So that's the interesting finding. So when we add the RGB to it, the results not necessarily better, or not significantly better. And the reason for that, we think, is because, remember I mentioned how good this system is to put together that point-cloud coloring, etc. So the SIRIS system has that coloring point cloud, one of the best out there. I don't think there's really much better out there technically to color point cloud. But in this environment, you got all these leaves and things. You got those sliders getting halfway through the leaf or halfway to the back. Some people know what I'm talking about. And then the coloring is just can be messy, can be really messy, and that can actually hurt you. So you win from the semantics, but you also lose from that. So in that case, we find that the added computational linear RGB is not worth it. Basically, just don't do it. But that's only if you get to a really good level of performance on the pure LiDAR information. So yeah, that was an interesting finding there. Okay, and just not going to stop it on this one, but just to say, when I was talking about earlier about we're trying to predict traversability by looking ahead and seeing what we see. There is limit to this, where you really need the proper reception. So that's an example where you don't know whether under this you have a slab of wood or not, and that visually doesn't make any difference. So how do you do with that? The only way you can deal with that is really to probe the terrain by using your proper reception and testing whether you have the resistance for your leg. That's all you can do there. I mean, that's not all. That's not true. To be fair, you could point a ground penetrating radar like on top of this, and you will probably see through. And yeah, fine, you can do that if you have the something. But then that causes other challenges. So the other way, just test, and then. So what we did with that work with CSIRO is basically the student developed a gate where you probe the terrain with you just put the force that you want to put on there. And you see how much resistance you get, and then basically as you come along with your other legs, you make sure that you step on the same spot and you don't put any more force than you have with the first time you went there with the front leg, and then keep going like this. This way you sort of reasonably safe with that. Of course, you have to. There's a bit more to it because you have to consider the fact that you know it's not exactly the same point. And, you know, it's like this. Okay. Any question, by the way? To interrupt, except you. Of course, you can ask a question. I may not be able to answer, but you can totally ask a question.
Yeah, so you're showing probing the ground as you're walking as informative, and you talked about using interaction with the greenery, with the shrubs to sort of self-supervise inference. What about putting that together and physically probing the vegetation to decide if it's traversable?
Yeah. Yes, that was the plan. What the student was going to get into. Normally, that was the objective. Didn't quite get to that, and we had an undergrad that was meant to develop that bumper. Course, yeah, didn't do a great job. So, but that's certainly on the cards. Yeah, that's what exactly what we want to do, and have a better understanding when you're looking at the vegetation. Understand what type of force you might have to put through. What orientation you might need to attack it. Sometimes that matters, like just attacking this from that front. Right here, we just assume we go forward and basically something push in that direction, but you could attack it from the side. Like, that does matter. So yeah, this is all on the card. And I have a student with Chris looking at some aspects like this of trying to reach crops through vegetation with an arm where you actually have to push things around, like so make your way through. And so how you attack it is going to matter for that. Yeah, that's all on the cards.
Great. Just maybe building on that, so underlying this, what you've presented so far in the forest scenario is a voxel representation of ultimately a binary traversable, not traversable decision, right? You mentioned just now kind of something might be traversable from different angles. There could be more like a continuous positive traversability in terms of time or risk of damage or something like that. Have you thought about kind of more expressive representations of traversability and how that could go?
Yeah, for sure. I mean, there is more information in there. We have plenty of information. So often, no matter what you keep, what's really matters, what makes a difference, what should you keep in there. But yes, that you have the type of information that then tells you that you have more chance of pushing this way than that way, or that how much resistance you're gonna get, etc. Like that's sort of what we want to get to. So, yeah.
Sorry, along the similar vein as Don's question, when you mentioned that earlier about the collision detector, collision, and using the probing to detect whether the vegetation is traversable or not, you mentioned using a force or pressure sensor on the front of the.
We wanted to use that, yes.
Right.
And we still want to, but
similarly, is that also implemented in the lagged probing part? Is there a force sensor on underneath it?
Yes,
I see. Just out of curiosity, having force sensors or pressure sensors at the bottom of lag robot has a tendency of breaking them faster than
Yeah, that's fair. I mean, for sensors, there's still some reliability issues with that. That's very true. And you want to have, it's nice to have, but you don't want to rely on that too much for a long period of time because I know they tend still to be, reasonably weak. So especially if you're going to step on vegetation and things like that. Like the example I showed in the lab and piece of paper, that's okay. But yeah, that's not only true. The less you can rely on that, the better. But that's improving the information you get from it, the reliability, and that's often how much money you put on it as well. But yeah, it remains a bit of a problem. Yeah.
So that's a lot of the current like quadruped and biped robots. They actually do pretty effective full body force control just using current from the motors. And,
Exactly. Yeah, I have noticed.
Yeah, there's limitation to that for the big sort of signals, like the obvious things, that's pretty reliable now, and it's more reliable than the sensors. Yeah. So there's a few things you can do. I guess if it's a matter of like it's going to collapse or not, you probably don't need the full sensor. If you want to know how much pressure you want to put in, that starts to be a bit more. Yeah, there's always when you use a torque of motors and all that stuff, there's always those gears that sort of give you trouble, and so you need to have some more. That's not the margin of your decision making out of this, but you can do quite a lot with this.
So we've been talking a little bit about like traversability and determining if something you can go through or not, but I guess traversability itself isn't necessarily binary. So sometimes maybe you can't walk through a tree, but you could force your way through a bush, or like you could fall down a hill and get through it, but maybe maybe you shouldn't have done that. So in those sort of situations, in the middle ground, how do you determine that was actually not traversable even though you got through it? Like, how do you make that decision, and can you do it online?
Yeah, I mean, you're absolutely right. And a lot of the traversability estimation, you come up with some kind of metric, which is a difficulty or traversal or something like this, where sort of 1 is an obstacle, you shouldn't go there, and 0 is piece of cake, and everything in between. And there's countless discussion on how that should be shaped, and what that means, and how to compare different approaches. It's a whole. Now, one of the approaches that are often taken, and you may argue that's valid or not, is when you do that probabilistically and you compute a probability of being traversable, then you can use that as a proxy for that difficulty that you're talking about, right? So if you absolutely dead certain it's an obstacle, because the probability of being an obstacle is 1, then you need not go there. If you have somewhere in between, that probably means that could be, there's some clarity on whether you can go through, because it's hard, but it's not dead center. So that's a way you can do that. I'm not saying that always translates into that difficulty, but that depends how you define it. And it often defined as a risk of not being able to traverse it, in which case that does apply reasonably well.
The NDT on the previous slide, was that normal distribution transform? Why did that work better than other representations?
Yeah, in this example, that's here. It's the SE and then with NDT. That was a combination of the two. That's a great question. I mean, it's already a pretty rich representation. We were surprised that in some of the cases we didn't need some of the other features. That was one of the surprises, and I guess thinking the SCNN does a good enough job to extract information out of that. Then you don't need all the sets. But I don't know how. It's one of those things. Like, I still think that if you add some of those features, that's going to be situations where you do gain from them. So for that particular test, I said it sounds like it would work better, but I don't know if generalize this. All right, briefly talking about this one, because I do want to talk about the Moonyard a bit after. So I'm going to tell that this is a fun project for doing a lot of jokes. It's a crack detection walls. All your horses, don't bring them those right away. My student probably found them all already. You can read the statistics, plenty of them. I had to limit it, actually. I had to tell me stop. don't ever do it. So yeah, the purpose of this was for mining initially, is like just to you have geotechnical experts that go into mine site, mine tunnel, and basically survey the cracks in the side. They're looking at the crack, they're looking at their width, they're looking at their length, they're looking at their organization in space to basically figure out whether it's going to collapse in 6 months or 2 years or an hour. So sending the idea of
We're going to miss the huddle here.
yeah, we're going to The idea to send a vehicle, a robot that has a scanner on it and basically do that job automatically would attractive, or at least bring up a report saying I found those cracks in that position, that orientation, all that stuff. As often we started thinking, oh, we're gonna take so back then we're gonna take a hover map and like that's it and do that out of this, etc. But that was not good enough. Has improved since then. So we ended up doing it mostly with a fixed sensor like a FAR that can give you a really, really nice scan, which does have to sit there and take that scan very accurately. And as always, if we can't do it with that, then we're not going to do it with a mobile vehicle. So we had to start something. So yeah, the process. So in this case, again, voxelizing for question of computation, and it's another sort of binary classification problem, crack, not crack. We do overlap those voxels also to get a bit better resolution. One of the interesting things is a crack is actually the absence of points. So that makes it tricky to define things when you detect the absence of something. See an example here and see the Kangaroo Point Cliff for the North Brisbane, a very popular place for climbing. You see some markings there, which you know that. Some of the cracks in red, and I guess give you an idea that's really hard to spot actual cracks in there. It looks like it's all cracking everywhere, but only some of those are. So yeah, obviously what we're finding is not the crack itself, it's the points on the edge of the crack. So you know, what does that mean? It's part of the challenge there. And so yeah, the deep learning for point clouds getting pretty good to do those things, although this is not the perfect application as such. Part of the challenge is when you label your crack, how far of the edge do you go? That makes a big difference. And then we try to find, once we find a reasonable amount of the points that belong to that crack, we try to estimate the orientation of the crack, the width, so width distribution, and especially the maximum width. And properties like this that tell us interesting things about the cracks. No, so we did that for an underground mine tunnel where so this one is relatively easy because it has shotcrete on it, so it sort of makes it somewhat. So the crack detection field is well known in civil engineering application where you have a nice wall and you have a road or something that's basically locally flat. But for non-structured things, rocks and things, bare surface like this is much more challenging. Now, when you look at these things, so you know, if you compute again the F1 scores and this type of scores on this, and by the way, we should have used MCC score on this one too, because again, the balance is not good. They're very unbalanced assets very often. You find, I guess you need to get a bunch of points enough to reconstruct, to basically get the characteristic of the cracks, but there's no need to find every single point of that crack. So it's like, you know, and there's no way you're going to get 95% of your points right. But how much do you need to be able to then give you a good estimate of the characteristics was one of the interesting questions that we ended up sort of trying to find an answer for. So, and it's I guess a lesson for us engineers. Often we're trying to tackle an application and ask my student, how good does it need to be for the application that you have? Because there's no point in trying to hit the 99%. That's not going to help, but in other cases, it's essential. So what do you need from that? And you can use the right system and tune it the right way so that you get performance that you want. So anyway, thanks for some pretty videos also. Okay, so yeah, excited to introduce to you the Space Lab. It kind of has a name, but it hasn't been officialized yet, so I can't tell you yet, but it's exciting. It's making its way through the university, BBC, like to take it off. So for the moment, we call it the QUT Space Lab or Lunar Testbed. And so it's essentially a moon yard, which will be probably turned into a Mars yard later on. Fairly large one. So this surface here is 19 by 11 meters. We have that massive roof on it so that we can use it with like normal sunlight for field robotic application, or we can, the idea is that we can also put curtain around and control the light. So we can sort of hopefully do both of those. And it's being built and it costs a fortune, and we got a little bit of that funded by the RC, 1.2 million, which is great. It's used a lot, but that's only a fraction of us. Yeah, we're trying to do a few challenging things. One of them is to use the crane, the overhead cranes, to lift some of the weight of the rover to do gravity compensation, which is something that sounds straightforward, but it's actually really hard. So we stopped picking on it. And I'll talk about the regulated simulant and why I put quotes on it. And also the idea is that, so this space we have, it's on this side, So half of this, we can open it on both sides. And the idea is that then we can basically do tests in there and come out and expand the test area on this side, do indoor, outdoor transitions and interesting things like that. And we have that high ceiling also to find flight drones, etc. Because you can totally fly drones on the moon, right? Not for this, but for Mars later or for field robotic application. Overhead cameras on top and all kind of things. And there's a team that's going to be based here, and it's a drone operating team that can sort of deploy from there as well. So yeah, it's quite a nice facility. We were just talking with Ian and Don doing more space stuff, and guys are interested in using this. So we also plan to have that available for some ambitious grant that we're putting in and send that as a facility we can use.
Is this at the main QT campus on the
This
river?
is unfortunately not at the city campus. This is on the Caribbean Grove campus, which is just 10 minutes north, a little bit out, because that's the only place where we have some space. Not a lot yet, but we have, we snatched a little piece of parking lot that it was not used, and it's like, okay, we're taking this. Believe me, we tried to get it at Gardens Point. We tried very hard, and we lost that battle. But that was the interesting thing of losing that battle is once we lost it, like because we really wanted it there, and they're like, sorry, you can't have that. But then because it's going to be there, what do you need to make it work? And then suddenly the budget, right? So that was a nice thing too. Yeah, so the idea is to test some of the things that are in the Space Agency roadmap, such as rover navigation and autonomy, especially, and also some of the tasks of landscaping the place, etc. So one of the dreams I have is that we can have that shape of the terrain, and then basically survey this and return it to the same configuration or change it in a very controlled way, and we can actually have robots do that. And then say we want to test in that configuration, the robot pass over that destroys everything, and then we want it back the way it was before, and we can do that all the time. Pretty hoping we're not quite there, but it's feasible, I think, but it'll take a bit of time. What else I'm going to say on this? There's working control room on this side there, large workshop, so we can do this. Overhead cameras covering the whole thing. Unfortunately, no motion capture in it yet, but that's one thing that could be added later. But the overhead cameras will have this, let us see where the robots are in the plane. This is what it looks like. So that was last week. This is what the place looks like on the outside. It's fairly big place. You have tennis court next to it if you like tennis. You can come to tennis afterwards. Our evil plan is that we plan to take over the tennis court later. Extend this side, and we can extend on this side. Also, there's another parking lot there, so there's plenty of room for expansion. You gotta be ambitious. That's the workshop next to it. And so it's pretty close to there. The building is pretty much going to be finished normally at the end of the year. Then furniture and stuff coming in January, and we can open actually it's up to the 6 early next year. So it's getting really close, which is exciting. These overhead cranes that we used to bring some rocks in and for the rover compensation, gravity compensation. Is the large door that open on the side was supposed to be the whole length, but we lost that battle again on the budget increase at some point. One of those things.
Is that a glass roof?
Yeah.
So for light control, are you planning on?
Yeah, that's one of the remaining questions. So like for initially we'll have curtains around there on the sides and do that at night. The top there is a question mark whether we can down the track cover it and like because with the crane and the cameras and stuff it is a little bit a tricky one. So when I asked them for that, they're like but I'm hoping we can get that sorted down the track. Yeah.
So Thierry,
Yeah,
that's
right.
Graham here. One of the issues with your safe regolith is going to be humidity, because obviously as it starts to absorb water, because that area is pretty humidity is pretty high. It's going to start clumping, and you won't get the static characteristics that you actually need with the regolith. So what are you going to do about that? Is it going to be air conditioned?
You're correct. Unfortunately, not, because it's a massive volume and we don't have that kind of resources. The Japanese have that air condition and stuff. Yeah, you are very correct. Interestingly, so if I have time, I can talk a little bit more about the regolith. So my student looked into the properties of the regolith and what we're going to put in there. And in some cases, humidity can play in our favor actually, and put that material closer to the properties that it has on the moon. So the humidity plays a role in there, and it's not always against you. But that obviously depends on the level of it. So there's going to be something there. Yeah, humidity is going to be an issue. Obviously, that's why we had it covered and not a pure outdoor thing in the first place, because in Queensland that's not viable. But there's going to be a challenge with humidity management. Yes. Yeah, briefly, so one of my students with a robotics student, I ended up doing a lot of geology, civil engineering stuff on his initial few months, because he wanted to find a recipe for that material that we put in the ammonia, which is close enough to the real thing. And so he did a lot of studies on this, and basically looked at having something that's so safe, practical, and cost effective. So the solar, because there are a bunch of, there's several formulas of simulant, of high fidelity simulant out there that people sell. They're very expensive and they're actually dangerous for you, because the real stuff is not safe to use, right? So we always had to play that game where like we just close enough without getting into the danger zone. And then, so with all the biomechanical property, what we're mostly interested in, of course, is the thermomechanics. So the rover going over, it's gonna react similarly to the real thing, right? So as close as possible. Now, the thing that people don't take much interest in usually is the perception. So not just the look, not so much the color. We're not that interested in the color aspect, but besides the grain distribution that gives you some of that texture, there's also things like the retro reflectivity of the material, how much light comes back when you give it, how that light gets polarized as you heat it, and things like that. And that's why we've tried to get closer to that all this happen, because I guess all this have not looked at from the robotic perspective of the section, which is a bit of a particular case for us. So yeah, pass you the detailed formula, but essentially this crusher dust, which is what most people use, but we add glass in it. So crushed glass and glass beads in it, both to get the distribution of particle size better, and also to get that activity. And to an extent, we expect that to help a little bit with that humidity problem like I was talking about, and noting that also that humidity on that crusher dust, a little bit of it can change your properties and get it in the right zone or off that zone in terms of the problems. So I'll pass the details of this, but essentially that's the particle size distribution for the crusher dust, which is usually used by most people, and that's ours, which is close to one of world samples. So it's that's kind of what we're aiming for. And so yeah, polarization, we looked into this because we're hoping to use polarization properties to basically anticipate the type of regolith you have in there and use for traversability estimation. because how much compacted it is depends on how old that thing is, and you may be able to. There are indications that we may be able to predict that from looking at those properties from afar. So that's what the student actually is going to do, but he had to come up with his own soil before even doing that. It's one of those things you don't plan and end up needing to happen. Yeah, that's basically that. Oh, I had a cool robot with a laser on it. That's one. It's actually a laser, the Raman spectroscopy, spectrometry, sorry, sensor that can tell you what material you're shooting at and as far as application, just to see whether it's a dangerous chemical, for example, or something like that. And we combine that with robotics to do a hazard map in the environment. And I'm sure Graham will be interested in that part as well, but no more time, sorry. Right. Well, but if you have questions, I think some of the academics have a meeting now, but the others can they ask questions.
Well, our meeting's in here, but we can take 5 minutes or so for questions, I think.
Let's go with the online ones first, I guess.
Yeah.
Do we have any questions online first? I think Graham's already ready.
Yeah, no more from me. I'll talk to Thierry about his ramen stuff later.
Sounds good, Graham.
Do we have more questions online? Do you have more questions offline?
Yeah. So again on traversability, traversability is sort of it depends on the type of robot you have too, right? It's much harder for a legged robot to push through a bush than it is for a tracked one. Is there any, if you're using some sort of learned features to learn that type of thing, you sort of really have to learn it for any type of robot, which is kind of difficult.
Yeah, I mean, absolutely. Like there's a lot of privacy with the estimation stuff that basically put the robot out of the equation and passing. I mean, it's so if you want to develop something that is generic that doesn't take nowhere in there, there's the characteristics of your robot that doesn't, right? Like that type of work I used to introduce with a robot I used called the Crusher. I was a CMU robot, for those who might remember that, some of you might. It basically was a beast that would just smash through trees and everything. And they were like, who needs obstacle detection? All we need is detecting the biggest ass rocks and biggest trees. So it's a piece of cake. The rest we can smash it. So, perfect example, right? It's like you do have to consider this. The idea is always to develop a method that has that in there, but then if you change the platform, you have to change your parameters or retrain your system, but use the same method, right? So in this, you have to label your data set with your robot, but the rest will happen just exactly the same way, right? Yeah. But if you change, if your robot is twice as big as ours, then we do that for sure. Then if you have a more explicit model, which you have in some cases, you might not need to return, you might just need to account for that different size and weight, and then basically adapt that model directly. That's also the way, but you do need the practice. Absolutely. Yep.
Another question. You mentioned a lot the challenges around obtaining ground truth if you want to do learning-based approaches.
Yeah.
Yes, in a lot of domains, people are looking at simulations and synthetic data.
Yeah.
Here, you're talking a lot about kind of things where the simulator would be granular physics or like vegetation bending and braking, and so it's fairly complex physics involved. Do you have a view on the use of simulations to generate ground truth? This is part of the data set, or
it's one of those things. So whenever it's like pure geometry, I think simulation does a great job nowadays, and there's no issue there. Appearance does better and better. Still some limitations. The physics. So the student I was talking about with Chris I spent a lot of time initially trying to get some simulator that would give us a reasonable behavior of the plants as you interact with them, and not just it's a nightmare. So as much as NVIDIA and others that develop this stuff, they're doing some really good things, but you either need like incredible computation just to make one tree and a couple of branches and the behavior, or simplify atrociously. And So yeah, it's still a very much a challenge of how much of that. I think we're getting closer, but still it's not very, very hard to get a behavior or that vegetation that is realistic physically. It's so hard. So yeah. So and there's still, again, NVIDIA and some others have put a lot of effort on that, but it's still not enough of a coordinated effort to get something, this company get there. Like Unity did their own thing, but it's not really always very open. Like, it's NVIDIA, even NVIDIA has like, I mean, when she started to look at, talk to Fabio, he said, yeah, I use this and that, we sorted that out. It's like they have 10 different versions of 10 different tools attached to like SIPs and blah, blah, blah. And it's just like, and all of them are bugged in. It's like you can spend your entire PhD on this, right? If anyone wants to do a PhD on this, please.
Yeah.
I didn't sell it well, but it's very interesting.
Yeah.
This is a question, I swear. You said RGB data didn't turn out to be informative in the traversability estimation in the forest. That's not what I said, but sorry, correctly, what did you say?
No, I said it does bring a level of information, but I said in the overall result, it doesn't always help to improve your, but it contributes some information in some cases and some confusion in others. So it's sort of, you could argue that it doesn't bring information. I would argue it does, but anyway.
Correct. Yeah. So the question is, have you considered some of the higher fidelity representations, visual representations, to help address the obvious gap there? So NERFs, for example.
Yes, we very much have, and that's one of those things I don't quite have the people to get onto that seriously, but that certainly has been, I mean, that was Nico's suggestion on this for sure, obviously. Yes, I think I'm still a little bit skeptical that something like NERF would help that much in that complex vegetation situation, even though it does look very impressive. It's filling the gaps in, I mean, I don't know, I honestly know very little about that. I'm gonna say something outrageous, but my feeling is that it's still kind of filtering up, but filling the gap between what you don't know, and you tend to do that in a way that smooths things out, and in an environment like this where it's all kind of all little plants and branches and things, I don't see how that would quite figure out what our problem is, because our problem is that intricate of and very, very kind of fairly random, and it's not like a structured environment where that would do marvels. Right?
With reflection and transparency, I agree with you. NERF is faking it, but with dense occlusion, it seems to be pretty good.
Yeah. I mean, I think that's certainly worth exploring, and that's something. Yeah, love to have someone looking at it, and we did ask the same question, and we'd like to know the answer. We just didn't have the resource to put on it. But you're right.
I guess that's it.
I had just one quick the paper demonstration was really interesting. I think if you extrapolate that out, you have a factory floor covered in paper, right? You don't infer from standing on the paper that it's safe. You infer that the floor is concrete, therefore it's safe to traverse across the paper. Is that logic sort of incorporated? Because there's like translation, of course, like a farm, pastoral land, right? You run across a paddock, but there is a risk that it could be like a rabbit hole.
Yeah, exactly. Yeah, what you don't see, and that's a danger, right? So, I mean, it's interesting you take the example. So some of that work was inspired, like there was a deployment of Lego robots in an old wooden abandoned sort of park, and it kept falling off because like you looked like you had that wood, but most of that wood was rotten, and regularly we just step on something and look totally fine and just goes through. So in case like this, you could infer this old wood actually it's all fine, but it's rot. So there's always that you can make that inference. We make that inference when we don't know better. We don't know what else to do, and that may be right or not. But you assume your property from the neighborhood is the same, and you make a mistake out of this because it's not. It has that extra aspect that is not observable that you trying to anticipate, right? Like it's under there, visually you can't see it. The context may tell you it's a bit rotten around here, but you don't know where exactly, unless you have that penetration. Again, either that test or that penetration with a with a a ground penetrating radar or something like this. I always want to put the ground penetrating radar, right? But every time I try, it's like it has to be exactly on top of what you're looking at, exactly like parallel to the surface and close enough and all that. And yeah, it's not often that you have that chance to.
I guess there can be, maybe to Kieran's question, contextual priors about the nature of the geometry, right? In a factory, you assume flat concrete floors.
Correct.
And then I was actually kind of also wondering, in the forest, when you're building these voxel maps from LiDAR returns, is there any kind of prior there that, there's an up direction and the ground tends to be kind of an undulating surface, and then there are isolated structures coming out of that? There's trees, or, would it estimate, if you tilted the sensor on its side or something like that, would it estimate things entirely the same, or does it know anything prior about like the nature of the ground?
So yeah, it's a great point. I would say it's kind of. I mean, it's a bit in there. It's not explicitly in it, that we don't make that assumption as such. But for first, the world is organized in voxels that are up here, and so that structure is there.
Yeah,
the ground is sort of not flat, but yeah. So that tends to be captured in this way. We don't. That said, we don't reason based on the position of that voxel. For example, it's higher up, it's lower up, something. But it does take into account some of the information and the surrounding of the voxel, right? So if you have a neighborhood that includes the ground versus one that doesn't, and things that does have indirect influence on the result. So I'd say some of that is captured, like implicitly. Not so much explicitly a little bit, but yeah. And you could potentially enforce that more or less, depending on tree trunk tends to be kind of up, and so that might help you. But they're reasonably easy to figure out what they are anyway. So I guess that you don't really need that. The hard one is the one that kind of tend to go in the direction. That's so, yeah. Cool. Thanks everyone.
Thanks, Thierry.